Dear colleagues, today we will talk about confocal Raman microscopy, basic principles and applications. As you know, Raman scattering was discovered almost 100 years ago, and since that time there are a lot of inventions has been introduced. For example, some new light source like lasers appeared, also charge coupling devices to detect spectra at a single shot. And here we can see first Raman spectra detected by the film. On the first top image you can see filtered mercury lamp spectrum, and on the bottom image you can find in addition to mercury lamp the benzene scattering spectrum. So what is Raman scattering? This is a vibrational technique, a process which happens when the light interacts with material. There are several ways how light can interact with material. For example, relay scattering. This is when the light absorbed by the material and then emitted on the same wavelength without any changes of the photon energy. Another possible way is adsorption. For example, infrared adsorption, when light fit to the energy levels distance and the photon energy is completely absorbed by the system, by the material. And in case of Raman scattering, there are two types of processes: Stokes Raman scattering and anti-Stokes Raman scattering. When first light is absorbed and then there is some interaction inside, and emitted photon has lower energy. This is so-called Stokes Raman scattering. And if emitted photon has higher energy, then it is anti-Stokes. On the bottom spectrum you can see Stokes has a stronger signal on the right hand side and longer wavelengths, so higher wavelengths. And anti-Stokes has low probability, that's why the peak's intensity is smaller. And you can see position of the peaks is very similar, so it's exactly the same numbers, and there are so-called wave numbers, which are energy units. They are directly proportional to the photon energy change. Okay, so Raman scattering is a very low probability process. Only 1 per 10 million photons interacts in that way to emit energy shifted photons, Raman scattered photon. And to suppress such a strong main excitation light, we need to choose proper filters and also, of course, proper lasers. So lasers are very common light source for Raman microscopy, and of course they are very helpful just because they have a very strong power and a very narrow spectral bandwidth. In this case, for the Raman scattering, typical excitation wavelengths are in the range from UV, like 405 and 473, 445 nanometers, up to infrared range, up to 785 nanometer or even 1064. So in visible range, typical there are green and red lasers, and what is important to know that the efficiency of such Raman scattering process is proportional to the force power of the laser frequency. And the shorter wavelength of the laser, the higher intensity, the higher probability of Raman process. And another thing you can see on this image, there is a fluorescence which almost always appeared when the light interacts with material, And of course, to avoid fluorescence, you need eyes that to have the wavelength which is not overlapping the fluorescence, or you should use some techniques which can make some photo bleaching or some other more complicated ways how to avoid interference between fluorescence and Raman scattering. So what about microscopy? The confocal configuration scheme, it allows to get X, Y on the right hand side and Z spatial resolution defined by diffraction limit. So you can see laser beam comes from the right hand side and focused on the surface by objective. If there is some signal comes from the material, from the inside of material, then when it goes to the confocal pinhole, it is not focused inside the pinhole, it is defocused spot, and then it's not affect a lot on the detected signal. So this is how we can separate signals from different Z position points. And when we talk about XY resolution, the point on the optical axis will go through the pinhole, and the point from the light from this point, from the other point, it is not going, the light not going through the pinhole, it is blocked by the pinhole, and detector is detect only area close to the optical axis. So this allows to us to get resolution about 0.5 wavelengths divided by numerical aperture. And the parameter called the numerical aperture is parameter of objective, how wide angle the objective can use to detect the light. So this parameter is written on each objective, and the higher numerical aperture, the better resolution you can get, and same time the stronger Raman signal you can achieve, because Raman signal emitted to the every direction, and the higher angle you collect the light, the better intensity you can get. So here you can see how the system looks like. It has two main modules. First one is confocal microscope, and the other one is upright microscope, which allows to scan, to select the different objectives, and to focus the light on the surface. And how it works, let's see on the flash model. So different wavelength lasers can be introduced by triple input port, and then the light is formed inside the confocal module to get a proper diameter of the light, collimated beam, and also proper polarization. Here you can control the laser power, and switching between lasers automatically allows you to change all the necessary units like filters, like beam expander, to prepare the laser beam of desired size. And on the way to the spectrometer, light from the sample goes through filters and focus to the pinhole, and after that it collects to the monochromator, to the spectrometer, equipped with several gratings with different dispersion, and then light can be detected by charge coupling device, by CCD, or by avalanche photodiode, for example, by point detector, which is mounted on the second output port after the spectral slit. So to summarize, we can say that such configuration allows to get diffraction limited resolution, which is down to 200 nanometers for blue laser with oil immersion optics. Also, the proper coatings of the mirrors and gratings allows to get about 70–80% of optical throughput, and full motorization gives us possibility to switch between a large number of lasers, 5 lasers for example, and fully automatically perform these changes. And different output ports allows not only perform Raman spectroscopy but also fluorescence imaging, also fluorescence lifetime, and some other advanced optical techniques. So this is a scheme of spectrometer configuration. You can see light goes from this pinhole, shutter can block the light, then the mirror reflects light to the parabolic mirror, then it goes to the grating, and then reflects to another parabolic mirror. So after the grating we have a dispersion in the angle, and to focus it on the CCD we use the second parabolic mirror, and could be focused to the CCD or avalanche photodiode. So for Raman spectroscopy it's very important to have high reproducibility and high accuracy of rotating such gratings, such motors who control the position of the grating. And also all the gratings and mirrors should be optimized for the selected spectral range. For example, when we talk about UV region, we should use aluminum coated mirrors which have about 80% efficiency down to 200 nanometers. When we talk about visible range, probably the most popular solution is silver coated mirrors with protected coating of CO2. And when we talk about infrared region, then of course gold coating is preferable. And selected grating also improve the efficiency. So there are different wavelengths of the so different gratings has optimized to the different spectral ranges, and it allows to improve the signal for selected excitation lasers. And there is also one special solution which we have in spectrometers. This is a Shelaev grating which operates not in the first order but in the higher order, like 66 or 55, something like this. And when we have such a grating, we can get a resolution down to 0.1 wave number. Here you can see each point corresponds to single pixel on the CCD, and the silicon peak has a lot of pixels, so we can get very high spectral resolution, which could be important to understand the material parameters like stress or strain in the silicon structures. When we talk about silicon, there is a direct relation between mechanical stress and a shift of the Raman peak position in the material. So not only research high-level research-grade microscopes can demonstrate such a high resolution, but also it's important for most of the microscopes. And here we can see a very compact design microscope from Aztec company, and it can demonstrate down to 4 wave number resolution for the green laser, and such resolution is typically good enough to recognize most of the spectra and detect some composition materials sample distribution. So you can see 0.2 nanometers for such system is quite standard parameter. And another important component of the Raman spectroscopy system is filters. So there are typically 2 types of filters which you can find in Raman spectroscopy systems. First is H filter, which is gray color curve, and they blocking the laser, which is zero Raman shift, which is zero energy shift, and it blocks with a high efficiency. The laser line is blocked about 6 orders, and the Raman signal is available starting from about 100 wave numbers. When we need to have both stocks and anti-stocks, for example curve number 1 and orange color, then we should use so-called notch filters, and they block some band around the laser peak position. And when there is standard filters, they block about plus minus 300 wave numbers, and the lines below the values about 200, 300 are blocked completely. And for the H filters, everything below, for example, some 70 wave numbers is also blocked. So to get them visible, such wavelengths, we should use a very special filters called Bragg volume filters, when there are a lot of layers in the single filter, up to 10,000 planes, and it allows to get a very high selectivity and block laser light with a very narrow band. So it allows to get access to the peaks which normally hidden when we use standard filters, and with such Bragg volume filters they are available, like sulfur spectrum, which you can see on this image. So of course software, here you can see the automatic software, fluorescence background subtraction, also automated spectral calibration by neon lamp source, and panoramic functions. They are very important. Let's talk now about some applications. First of all, when you put your sample on the microscope, what you need to know is what is the Raman spectrum from selected point. And here you can choose point on the optical image and get spectrum. For example, here it is a molybdenum disulfide on the surface of silicon. What else can we get from Raman spectroscopy? For example, for carbon nanotubes, we can identify the single wall nanotubes and multi-wall nanotubes, and also if it is a single wall nanotube, then by the RBM, radial breathing mode, we can identify the diameter of nanotube with a very high precision, which is about 0.1 nanometer. And for mapping, we can get distribution of the intensity for selected peak. When you choose, for example, peak which relates to carbon nanotube and make mapping, then you can get the position of your nanotubes on the surface. And for graphene, you can see clearly there is a difference between single layer and two layers and multi-layer graphene. And to get some information, also you can use both stocks and anti-stocks, and it is possible to calculate a temperature of the sample by the ratio between stocks and anti-stocks components of the Raman spectroscopy, of Raman spectrum. And here there is an example of detecting temperature distribution for the electric circuit, when the floating graphene, and there is a floating graphene and there is a current flows through this graphene layer. Also mechanical stress, as you remember, can provide shift of the Raman spectrum and also make the peak not so sharp. In this case it is a diamond crystalline material, and on the edge of crystallines there is a mechanical stress. You can see a red curve which makes the peak width, which makes the peak broader, and peak position changes also a little. For pharmaceutical applications, it's important to know that all the components in the tablet, that they are uniformly distributed for the whole tablet. And this is example of aspirin and paracetamol material inside the single tablet. For polymer blend, we can also identify different composition polymers by Raman scattering. If we choose selected peak which corresponds to different polymer, we can get a map and clearly resolve position of different type of polymers. And of course, not only XY mapping can be done, but also XZ, as you can see here, when it's important to know what is the thickness of coating layer. And the red spectrum with a peak about 2930 wave numbers, it corresponds to the silicon coating, and tablet body is a green color. So such cross-section gives information about the structures in Z direction. And also for polymers layer, for example, packaging, it's important to know what is the thickness of different layers and if they are stacked together properly. So here we can see profile of such coating. And some 3D objects like polystyrene microsphere can be also resolved easily, and the resolution is extremely high for immersion optics. Here you can have about 200 nanometers for XY and 500 nanometers in Z direction. On this image you can see a fluorescence 3D imaging. So not only Raman can be done with the same signal system, but also a fluorescence, because it has spectral range also in the same positions where Raman peaks appears. And simultaneously it's also possible to perform Raman and fluorescence imaging. You can see on the spectrum there are some peaks, relatively small peaks. On the left hand side there are blue color band for detecting the presence of material, a blue color peaks, and this image corresponds to distribution of such peaks. And the other peak, a red color, orange color peak on the spectrum, it corresponds to the fluorescence which appears only in monolayer material, but in bilayer or multilayer it's significantly smaller because of the type of semiconductor in this case. So this is molybdenum diselene flakes, and such optical properties can be identified simultaneously with the Raman mapping. And as I said, also we can do fluorescence lifetime imaging. For example, here there is an image of bacteria, genetically modified bacteria, and they produce fluorescent labels which have very similar fluorescent spectrum, but quite different lifetime. And that's how we can separate different type of bacteria by the fluorescence lifetime map on the left hand side. And also to get fast and reproducible scan images, it's important to use proper driver, proper scanner. What are the type of scanners which we can use? Of course, most popular is motorized scanning stage. Normally it has resolution about 100 nanometer. A step size of the scanner is 100 nanometer, but it allows to scan a very wide scanning range, several centimeters, something like this. And another option is piezo scanner, which has limited scan range, maybe 100 microns, 100 by 100 microns, but it has a very small step size. And here we can see an example of scanning by XY piezo stage, and it allows to make resolution 200 nanometers and quite easily to perform such scanning because step size is below 1 nanometer. And with galvanic mirrors we can get a very fast mapping because sample is fixed. We should not move sample at all, the laser spot is moving. Here we can see the process how to choose proper peak. This is silicon peak at about 520 wave numbers. Then the wavelength, you can see it's about 654 nanometers. So the red laser is excitation laser. We should choose another port for the fast detector. If we have enough signal, if we have very fast detector, then we can do Raman mapping really fast for the selected band. And we choose 30 by 30 microns and 150 by 150 points. And to get a single map, it takes about few seconds for the whole image, which is really fast for such low intensity signals which normally Raman has. So this is a structure on the silicon O2 configuration, silicon O2 sample, and it takes less than 5 seconds, only 3 seconds to get such a map. Okay. So to summarize, I would like to finish the presentation with this slide, and I hope that confocal Raman microscopes from Ostec company can help to solve a lot of various Raman applications and can satisfy any budget. Thank you for your attention. Goodbye.